Have you ever wondered if AI could truly learn and adapt on its own? Not just execute what has been taught, but actually evolve its own capabilities, almost like a living organism,
Yeah, imagine an AI that doesn't just stay static, but gets smarter, more capable.
and even invents new ways of doing things based on its experiences. It's a wild thought. So today we're taking a deep dive into self-evolving agents. And this isn't just, science fiction
Not
anymore.
at all.
It's a rapidly advancing field, and it signals a pretty fundamental shift in artificial intelligence. Our mission today, we want to unpack what these agents are, how and when they learn to grow, where they're already making a real-world impact.
Which is quite surprising already.
Right. And how we even begin to measure the progress of systems that are constantly changing. We're drawing our insights from a really comprehensive survey paper that pulls together the very latest research.
And what's truly fascinating here, I think, is the journey we're seeing in AI. We started with large language models,
Right.
LLMs, which are incredible, don't get me wrong.
Yeah.
But they are essentially static. They're like brilliant encyclopedias that, well, they don't update themselves.
Okay.
Now we're moving towards these dynamic, continually adapting systems. And this isn't just some incremental upgrade.
Oh.
It's a conceptual path. It points towards what some envision as artificial superintelligence, ASI. Systems that could potentially operate at or even above human-level intelligence across a huge range of tasks.
Wow.
It's really the shift from static knowledge to dynamic, self-improving intelligence.
Okay, let's really unpack that then. The core limitation you mentioned, the one self-evolving agents aim to overcome, is exactly that static nature of traditional LLMs.
Precisely.
They just can't adapt their internal workings, their parameters or behaviors when they hit new tasks or new knowledge or, dynamic situations.
Right, and that creates a real bottleneck for using them effectively in messy, open-ended, real-world environments.
So how does a self-evolving agent fix that?
Well, fundamentally, it's a system designed to continuously learn. From new data, sure,
Yeah.
but also from interactions, from experiences, and critically, doing this in real time.
Okay, real-time learning.
Yeah. And it's not just about piling up more data. It's about evolving the agent itself, leading to AI systems that are more robust, more versatile, and ultimately far more capable of tackling those complex, dynamic problems we see in the real world.
So how are these agents actually built? What are the components?
Good question. You can think of an agent system as having two main parts.
Yeah.
There's the environment it operates in
Right.
and the agent system itself.
Okay, the environment first. You mentioned it's often modeled as a POMDP, partially observable Markov decision process. Sounds complicated.
Sounds technical, yeah, but the concept is intuitive. Imagine you're trying to navigate a dark room with just a flashlight looking for something specific.
Okay, I can picture that.
You take actions, right? Move around, point the light, but you don't see everything at once. It's partially observable. You get feedback, maybe sounds, maybe you bump into things, telling you if you're getting closer or further away.
Right, like getting warmer or colder.
Exactly. That's essentially the world an agent operates in. It has goals, like finding the object. It takes actions, which could be internal reasoning, like thinking, where did I last see it? Or external, like calling a tool or asking for information. And it gets crucial feedback or rewards.
And the agent system itself, what's inside that?
That typically combines an underlying LLM or maybe a multimodal LLM,
Okay.
essential context information like the prompts guiding it and its memory of past events, and then a set of available tools or APIs it can use to interact with the outside world.
Makes sense. But how do these self-evolving agents really differ from other AI learning approaches we've heard about? Like curriculum learning or lifelong learning.
That's a key distinction. Their dynamic, active, and autonomous nature really sets them apart. Take curriculum learning, for instance. It's about presenting data in increasing difficulty, sure, but it usually operates on static data sets and mainly updates the model's underlying parameters.
Right.
Self-evolving agents, though, they handle sequences of tasks and environments that are constantly changing, and they can modify more than just parameters like their memory or the tools they have access to.
Okay, so more flexible. What about lifelong learning? That sounds similar, learning continuously.
It shares the goal of continuous learning, absolutely, but lifelong learning often focuses primarily on updating model parameters and tends to acquire knowledge more passively, often based on external feedback.
Passively.
Self-evolving agents are, well, more proactive. They actively explore their environment. They can use internal reflection to figure things out and improve themselves. It's a more agentic process.
And model editing or unlearning?
Those are much more targeted. They aim to precisely modify specific bits of knowledge within the model. They generally can't change the agent's broader behavior, its non-parametric parts like memory, and they usually rely on predefined pipelines. Self-evolving agents, on the other hand, can spontaneously pull out diverse and flexible strategies to adapt.
This is fascinating. So to achieve this continuous self-evolution, you're saying agents can evolve along 4 fundamental pillars: their models, context, tools, and architecture. Let's dig into those. Maybe start with evolving context. That sounds crucial.
Absolutely. The context pillar is fundamental because it shapes how an agent behaves moment to moment. It really guides its responses and actions. It has 2 critical parts. First, memory evolution.
Memory. How does AI memory evolve?
Well, agents are now being designed with long-term memory mechanisms that don't just store information, but actively adapt. Think of systems like SAGE. It actually uses a concept similar to the Ebbinghaus forgetting curve.
You mean like how humans forget things over time?
Exactly. It uses that idea to prioritize what information is important to retain and what can fade away. Or take MemL and has this 2-phase process to manage its knowledge base. It can add new facts, sure, but it can also merge related info, update existing facts, or even delete things that seem contradictory, all to keep its mind coherent.
Wow, actively curating its own knowledge.
Right. And then you have agents like Expel. It doesn't just remember past interactions. It processes them to generate insights and rules. It's literally turning one-time experiences into long-term skills or competencies.
Like learning from mistakes, but on a whole different level.
Precisely. It's about extracting deeper wisdom from experience.
Okay, that's memory. What's the other part of evolving context?
Prompt optimization. This is super interesting. Here, agents refine the instructions they feed to their own backbone LLM.
So they're tweaking their own instructions.
Yes, and this directly changes their behavior, but critically, without actually modifying the underlying model's weights. It's like learning how to ask better questions of yourself.
How does that work in practice?
It can be treated like a search problem. Agents can iteratively rewrite their own prompts, guided by feedback on how well those prompts worked. Think of ORPO, for example. It's almost like a continuous process of self-correction on their internal instructions.
So they learn to prompt themselves better.
Exactly. And this can get quite sophisticated. It can extend to optimizing entire workflows involving multiple LLM calls, like in systems such as DSPI or TextGrad, tuning the whole process for a global goal. Or even in multi-agent setups, where agents dynamically suggest and revise each other's role prompts to improve teamwork. Systems like MA0 or Evo Agent do this.
That's remarkable. So they can improve their internal thinking, how they instruct themselves.
Yeah.
And you also mentioned evolving tools. That leads us to the evolving tools pillar. This sounds like a huge leap.
It really is. This is an exciting shift from agents merely using predefined tools to actually becoming autonomous toolmakers.
They build their own tools.
Yes. This gives them incredible flexibility to innovate on demand, to tackle complex problems that maybe their initial designers didn't even foresee.
It's like, I don't know, your smartphone suddenly deciding it needs a new app to solve a problem you didn't even know you had, and then just building it itself.
That's a great analogy.
Yeah.
And it happens across a couple of interconnected fronts. First, there's autonomous discovery and creation.
How do they discover or create tools?
It can be through emergent trial and error. Think of Voyager in Minecraft. It autonomously explores the game world and builds up this huge library of skills and behaviors, essentially creating tools as it goes.
Wow.
Other systems might reactively search code repositories online or even write entirely new functions from scratch when they hit a capability gap. Systems like Alita or ATLAS do this. Some frameworks like Creator or SkillWeaver even try to structure this process, separating the abstract idea of a tool from its concrete implementation.
That sounds incredibly powerful, but also maybe a bit risky if they're writing their own code.
Absolutely. Safety and security are huge considerations here. Robust, automated verification becomes critical to ensure they're building reliable and safe tools.
Okay, so they create tools. What's the other front?
Mastery through iterative refinement. Because, let's face it, a newly created tool or piece of code is often buggy or fragile.
Right. First drafts are rarely perfect.
Exactly. So, methods like LearnAct and DRaft set up these self-correction loops. The agent uses the tool, gets feedback, maybe a compiler error, an unexpected API response, or just seeing the effect in the environment, and then analyzes that feedback to debug its own code or refine the tool's documentation.
So they teach themselves to use their own creations better.
Yes, and crucially, they learn to fix them. This helps tackle what researchers call the credit assignment problem. When a whole process fails, how do you figure out which specific step or tool use caused the failure? Analyzing that feedback helps them pinpoint and fix the root cause. Human collaboration can also really speed up this mastery process, by the way.
That makes sense. So agents can evolve their memory, their prompts, create tools, and the last pillar was evolving architecture. They can redesign themselves.
In a way, yes. This is where agents treat their own internal logic or even their collaborative structures in multi-agent systems as components that can be optimized. It's a fundamental shift towards self-enhancement.
It sounds like they're optimizing their own brain structure on the fly.
That's a good way to think about it. And this happens in a couple of ways. For single-agent system optimization, it might involve refining individual LLM calls within a relatively fixed structure. Systems like TextGrad use something called textual gradients. Think of it like back-propagating feedback through text instructions rather than just numbers.
Okay, textual gradients.
But it can be even more profound. Some research looks at optimizing the agent's high-level architectural design itself, like in Agent Square. And then you have the really radical approaches, like the Darwin-Gödel machine or the Gödel agent.
You mentioned those earlier.
Right. These systems are designed, conceptually at least, to directly modify their own source code.
A program that rewrites itself. That's mind-bending.
It absolutely is. And then there's multi-agent system optimization. Here, the focus is on how groups or teams of agents organize themselves and communicate.
So optimizing the team, not just the individual.
Exactly. This can involve optimizing explicit workflows, like how information flows between agents. Frameworks like AutoFlow or GPT Swarm do this. Sometimes the system design itself is treated as a search problem. ADACE or AFlow use techniques like Monte Carlo tree search to find the most effective team structures.
Wow.
And it also includes scenarios where multiple autonomous agents co-evolve their internal behavioral policies simply by interacting with each other. This can lead to emerging capabilities like sophisticated coordination or dynamic task delegation, which you see in systems like RIMA using multi-agent reinforcement learning or GGPO.
This is all incredible. Which brings us to a really key question. When does all this evolution actually happen? Are they constantly tweaking themselves, or do they stop and learn between tasks?
Great question. It clarifies the temporal dimension. And the answer is, well, both. Learning can happen during a task, which we call intra-test time self-evolution, or between tasks, which is inter-test time self-evolution.
Okay, so intra-test time is learning on the spot.
Exactly. These are adaptive processes that occur during the execution of a task. The agent hits a roadblock on a specific problem, recognizes its limitation, and initiates some kind of targeted learning right then and there.
Can you give an example?
Sure. Think about using in-context learning, ICL. Agents like Reflection, Ada Planner, or Trust Agent use their context window almost like a dynamic scratch pad. They employ self-reflection mechanisms during the task to analyze their performance so far and guide their next decisions within that same task.
They're realizing mid-task, okay, that approach isn't working. Let me rethink based on what just happened.
Precisely. Another way is through immediate supervised fine-tuning, SFT, where models perform quick self-edits, triggering small weight updates to adapt specifically to the current task context. Or even using reinforcement learning, RL, on demand, like the LDETR system, which generates focused subproblems to quickly learn a needed capability when stuck.
Okay, so that's learning during the task. What about inter-test time? Learning between tasks.
Right, this is learning that happens retrospectively after a task is completed but before the next one starts. It leverages accumulated experiences to improve future performance.
So like reflecting after the fact.
Exactly. It allows the agent to consolidate experiences and refine its overall strategies or knowledge without the immediate pressure of solving the current problem. It's like a sports team reviewing game footage after the match to plan for the next one.
How does that work?
Again, it's different techniques. With ICL, past task results, feedback, maybe successful workflows from previous attempts, are stored and retrieved as useful context for future, similar problems like in ICRL. With SFT, you have methods like self, star, or quiet star. These often involve the agent generating synthetic data based on its past performance. Maybe it failed a reasoning task, but later figured out the right answer. It can then generate explanations for the correct answer and use that as new training data to fine-tune itself.
So it creates its own practice problems based on its mistakes.
Essentially, yes. And with our ARL, inter-test time learning often involves more extensive optimization through environmental interaction, maybe during a pre-deployment phase or offline refinement period. Think of systems like Raygen, Distill, or Weberall Learning Web Navigation, or Digrow Learning Device Control through lots of simulated practice.
It's clear they can evolve their structure, their tools, their memory, and do it both during and between tasks. So what are the actual mechanisms? How do they make these improvements? What strategies are they using?
Broadly speaking, there are three major families of methods driving this self-evolution strategy. The first is reward-based self-evolution.
Based on rewards, okay, like reinforcement learning.
Related, yes, but broader. It centers on designing and using reward signals to guide that iterative self-improvement. And the rewards can come in different forms. You have textual feedback, which is really powerful.
Using language as the reward signal.
Sort of, yes. Leveraging natural language critiques, suggestions, edits. Think of systems like reflection, self-refying. It provides detailed, interpretable instructions for how to improve, like a coach giving specific feedback.
Makes sense. What other kinds of rewards?
There are internal rewards. Here, the agent exploits its own internal signals, like the model's probability estimates or its expressed certainty about an answer. CISC and self-rewarding language models use this. It allows guidance without needing explicit external labels.
So the agent judges itself.
In a way, yes. Then, more traditionally, you have external rewards derived from sources outside the model. This could be feedback from the environment. Did the action succeed? Maybe majority voting if you run multiple attempts, or explicit rules defined for the task, like in SuperDev or Sika.
Okay.
And finally, a really fascinating area is implicit rewards. Here, agents seem to learn from feedback signals, even when those signals aren't explicitly marked as rewards. It suggests an inherent capability to interpret subtle cues about success or failure. Some call this reward is enough, or endogenous reward.
Interesting. So that's reward-based. What's the second family?
Imitation and demonstration learning. Here, the agents improve by learning from high-quality examples or demonstration.
Learning by example.
Exactly. And this can happen in a few ways. There's self-generated demonstration learning, where agents actually create their own training data through iterative refinement. Imagine an agent struggling with a reasoning problem, eventually finding the correct solution path, and then using that successful path as a demonstration to train itself like STAR does for reasoning, or similar ideas in multimodal self-training.
So it teaches itself from its own successes.
Right. Then there's cross-agent demonstration learning. Here, agents learn from demonstrations provided by other agents, maybe more capable ones within the same system, or from external sources. Sirius uses this for multi-agent reasoning.
Learning from peers or experts.
Precisely. And finally, hybrid demonstration learning, which, as the name suggests, combines both self-generated and external demonstrations to get more robust training data. RISE uses this for recursive self-improvement.
Okay, rewards and imitation. What's the third family?
Population-based and evolutionary methods. These draw inspiration directly from biological evolution and collective intelligence. They often involve maintaining multiple variants of an agent or multiple agents simultaneously.
Like survival of the fittest, but for AI.
Kind of, yeah. For single-agent evolution, you might have multiple variants of an agent competing or being modified over time. We talked about the Darwin-Gödel machine modifying its own code. That's an extreme example. Genome applies genetic algorithms. Or methods like SPIN use self-play, generating multiple possible futures or rollouts and learning from the best ones.
And for multi-agent evolution.
Here, the focus shifts to evolving entire teams or networks of agents. This can involve evolving the system architecture itself, like EvoMac, which mimics neural network training principles but for multi-agent systems. Or Puppeteer, which evolves coordination strategies for teams. It can also be knowledge-based evolution, like MDTeam GPT using shared knowledge bases, or Metagent Sim evolving clinical interactions.
That's a really wide range of methods. Are there other dimensions that cut across these?
Yes, absolutely. Several important dimensions further differentiate how these methods work. One is online and offline learning.
Right, we touched on this with the when.
Exactly. Does the agent learn continuously while interacting live with the environment? That's online, like Voyager refining its skills as it plays Minecraft. Or does it process batches of historical data retrospectively? That's offline.
Makes sense.
Then there's on-policy and off-policy learning, mostly relevant for RL-based methods. Does the agent learn strictly from experiences generated by its current strategy or policy? That's on-policy, like reflection. Or can it learn from experiences generated by older versions of itself or even other agents? That's off-policy, which can be more sample efficient.
Okay.
And finally, reward granularity. How detailed is the feedback signal? Is it coarse-grained, outcome-based, just did you succeed or fail, like in DPO? Or is it fine-grained, process-based, assessing each step along the way, like MathShepherd does for math problems? Or maybe a hybrid approach? The granularity really affects what the agent learns.
So, with all these incredible ways for agents to evolve themselves, what does this actually mean for the real world? Where are we seeing these self-evolving agents being applied right now? Where are they making waves?
They're definitely starting to show up across a diverse set of domains. We can kind of group the applications into two buckets: general domain evolution and specialized domain evolution.
Okay, general first. What does that look like?
This is about designing agents for broad, versatile applications, especially thinking about them as general-purpose digital assistants. Here, sophisticated memory mechanisms are key. Think about Mobile Agent E, designed for smartphone tasks, remembering things across different apps, or Mobile Steward, handling cross-app instructions, or those generative agents simulating human behavior by storing and retrieving experiences.
So, assistants that remember you and what you do.
Exactly. And curriculum-driven training also plays a big role here. We mentioned WebRL learning web navigation with a self-evolving curriculum, or Voyager building up that huge skill library in Minecraft through self-directed exploration and learning.
Okay, so general assistants getting smarter. What about specialized domains?
This is where agents are tailored to get really good at specific, often complex tasks. We're seeing traction in several areas, in coding, for instance.
Ah, coding assistants that actually improve themselves.
Yes. Agents like Sika or Agent Coder that can autonomously edit their own code base to fix bugs or improve performance. Or Evomac optimizing how multi-agent coding teams collaborate. Imagine a tool that doesn't just suggest code, but actively refines its own suggestions over time based on whether they worked.
That would be amazing. What else?
Graphical user interfaces, GUI. Agents that can directly manipulate what you see on your screen, desktop apps, websites, mobile apps. Systems like Navi tackling Windows challenges, WebVoyager automating web tasks, mobile use learning smartphone operations, often by learning directly from interaction failures.
So, automating complex computer tasks.
Right. Then there's the financial sector. Agents like QuantAgent or trading agents are being developed to iteratively refine their responses, automatically enhance their domain-specific knowledge bases, and even continuously improve trading strategies based on real-time market conditions.
High-stakes stuff.
Definitely. And education is another really interesting area. You have personalized tutor agents like Pacey that adjust their prompts and teaching style based on individual student profiles, or systems like MathVC simulating virtual classrooms, or platforms where agents collaborate to critique and enhance educational materials, like EduPlanner for lesson plans or CFEL for generating homework feedback. It's about driving better, more personalized learning experiences.
That sounds incredibly promising. And you mentioned healthcare briefly.
Yes, it's another domain where self-evolving agents, particularly multi-agent simulations, are being explored. For example, modeling realistic clinical interactions for training medical professionals or for biomedical research discovery. The potential is huge, though obviously safety and reliability are paramount there.
Absolutely. Okay, this sounds incredible, but it also brings up a really tricky challenge. How on earth do you evaluate systems that are designed to constantly change? Traditional benchmarks seem like they wouldn't capture the whole picture.
That's a crucial point, and it's a major focus of research right now. Static, one-time assessments definitely fall short. We need a more comprehensive framework, really looking at 5 core dimensions to get a holistic view of a self-evolving agent.
5 dimensions. Okay, what are they?
First, adaptivity. This measures how well and how quickly the agent improves its performance on tasks within its domain through experience. You might track metrics like success rate by iteration steps or adaptation speed.
Okay, does it get better? Makes sense.
Second, retention. This is critical. It's the agent's ability to remember what it previously learned and, crucially, to avoid catastrophic forgetting.
Forgetting old stuff when learning new stuff.
Exactly. Metrics here include forgetting, FGT, which measures the drop in accuracy on old tasks after learning new ones, and backward transfer, BWT, which looks at whether learning new tasks actually improves performance on old ones.
Important for stability. What's third?
Generalization. Can the agent apply its accumulated knowledge and skills to new, unseen domains or tasks that it wasn't explicitly trained or evolved for? This is often assessed through aggregate performance across diverse test suites or specific out-of-domain tests.
Can it handle novelty? Got it. Fourth.
Efficiency. This quantifies the cost of evolution. How much compute does it take? How much time? How many interactions or steps? Token consumption is a big one for LLM-based agents. You might also look at tool productivity. How much benefit do you get versus the cost of using or creating tools?
Right. Is the improvement worth the resources? And the fifth dimension.
Safety. This is absolutely critical. It examines whether the agent develops unsafe, harmful, or otherwise undesirable behaviors throughout its continuous evolution. Metrics here include things like safety score, harm score, completion under policy, does it follow safety guidelines, risk ratio, refusal rate for harmful requests, and leakage rate for private information. This is purely about technical safety and alignment, not broader ethics.
Okay. Adaptivity, retention, generalization, efficiency, and safety. That's comprehensive. How are the actual ways we evaluate them changing the paradigms?
Well, static assessment is still useful for snapshot performance checks, using traditional benchmarks like SWE Bench for coding or Agent Bench for general tasks.
Okay, the old way still has a place.
Yes, but we're seeing the rise of short-horizon adaptive assessment. These benchmarks, like Memory Agent Bench, which looks at test time learning, specifically evaluate how agents adapt and improve over a relatively short period or a limited number of interactions.
So measuring the initial learning curve.
Exactly. But the real frontier, and the most crucial for truly understanding these systems, is long-horizon lifelong learning ability assessment.
Lifelong learning assessment.
Yes. This is about evaluating continuous knowledge acquisition, retention, and reuse across diverse environments over extended periods. It's much harder to do. New benchmarks like LTM Benchmark for long-term memory and Lifelong Agent Bench focusing on sequences of interdependent tasks are starting to emerge to tackle these complexities. This is where we really see if an agent can genuinely grow and maintain its capabilities over time.
That makes perfect sense. So looking ahead then, what does this all mean for the future? What's next for self-evolving agents? What are the big open challenges, the really promising directions we should be watching?
There are several really key areas driving future research. A crucial goal is to personalize AI agents effectively, making them truly adapt to individual users, your unique behavioral patterns, your preferences.
Like an assistant that really gets you.
Exactly. But this involves challenges like the cold start problem. How does it personalize when it has very little data about you initially? And ensuring that personalized planning, execution, and generation are effective and, importantly, unbiased.
Right. What else?
Achieving robust generalization is another major hurdle. It's this fundamental tension. How do you make an agent highly specialized and effective at certain tasks, while also maintaining broad adaptability to new situations? This involves designing scalable architectures, figuring out better ways for agents to adapt across domains, maybe through test time scaling, managing that continual learning problem to avoid catastrophic forgetting, and improving how knowledge can be transferred between agents.
A lot to tackle there.
Definitely. Then there's safe and controllable agents. As these systems become more autonomous, ensuring they don't develop unsafe or undesirable behaviors is paramount.
We talked about evaluating safety.
Right, but this is about building them safely from the ground up. Addressing risks from users giving misleading instructions or risks from the environment like malicious content. Improving their ability to even recognize sensitive information. Developing safer training algorithms and perhaps clearer agent constitutions, sets of rules or principles they must adhere to.
Agent constitutions, interesting.
And finally, the unique challenges presented by ecosystems of multi-agents. When you have many self-evolving agents interacting,
Things get complicated fast.
extremely. How do you balance individual reasoning with effective group decision-making? How do you prevent problems like groupthink or over-reliance on consensus? How do you develop efficient frameworks for dynamic collaboration where roles might shift? And critically, we need new dynamic benchmarks that can actually evaluate how these teams adapt and evolve over time, not just individual agents.
Wow. Okay, we have covered an incredible amount of ground today. We've journeyed through the world of self-evolving agents, highlighted their really profound potential to transform how we interact with AI across everything from coding and finance to education and healthcare. This deep dive, I think, really shows we're moving far beyond static AI tools. We're heading towards systems that embody a truly dynamic intelligence, systems that are learning how to learn, adapting to new challenges, and even, remarkably, building their own tools.
And maybe a final thought to leave you with. Consider what it truly means for the future, when AI systems can not only solve the problems we give them, but can also continuously re-engineer themselves to become fundamentally better at problem solving, often without direct human intervention. What new kinds of challenges, but also what incredible new opportunities will that unleash for all of us?
That's a powerful question. I encourage you, our listeners, to reflect on how these evolving capabilities might impact your world, your work, and your industry in the coming years. It's certainly something to keep a close eye on.